Welcome to our next round of seminars in the series, in the lecture series on genomics of health and well-being. We have had a few seminars in the past few months, and today we are fortunate to have Professor Sushanta Banerjee with us. So may I please request Professor Anupam Basu to kindly introduce our speaker today.
Thanks, Almura. Good morning, everybody. I'm very thanks to introduce you to Professor Sushanta Banerjee. Professor Banerjee currently is a scientist, VA Medical Center, University of Kansas. He did his MSc from University of Bardhaman and then PhD from Calcutta University, and then he went IISc and then the USA to raise software research career and the faculty members. He has a long career of research. He has an illustration of numbers. I am not going to numbers data to tell you number of paper being published, number of student being post-graduated or PhD graduated. But I'd like to mention that he has a regular grant reviewer of the NIH, also other international funding agencies. He is also the published paper like prestigious journal like annual number in JBC, Cancer Research, then PNS, and many more. And he is also patents, got a lot of patents in his credit. Just we have a chat with him in the just right now. I'm going to share with you the young students and scholars. We, the scientists, always worship the goddess Saraswati. We don't have a Loki with us. That's me. But he told just like before, he has one of the pioneer to show the aspirin work for the cancer therapies. And from aspirin, he brought the Mercedes bench. So the story. So that's the scientist. If you look work, you also get Lakshmi also. Okay. And he has a discoverer of lots of molecules, CCN group of molecules, patents, and not taking much more time. So over to Professor Banerjee to give you a talk today.
Good afternoon, ladies and gentlemen. Can you hear me? A nice introduction. Yeah, sometimes luck work to get money and education together. It's a trick, it's a politics. Okay, to keep together Lakshmi and Saraswati. So if you have daughters, you have both Lakshmi and Saraswati in your house. If you have a son, you can think about it. Okay. So yeah, it's true. Daughter is asset. Liabilities. So I'm lucky. I have two daughters that they are very good. Okay. They give my gift. They always give me gift every Father's Day. Use my credit card. So ladies and gentlemen. It's not working. This one?
Only the laser pointer.
Oh, is it loud? Okay, great. Thank you. So the title of my talk is the role of CCN1 in progression of pancreatic cancer. So I have to give a declaration of the conflict of interest. No conflict of interest. Why? Because I have some money from different companies. And also I just opened a new company that's called Lenexa Biosciences, and I'm not taking any money from them to give this talk. So I have to say no conflict of interest. Next, the main contributor of this work is my wife, Snigdha Banerjee. Without, oh, that's it. Okay, can you hear now? So her contribution is exorbitant. I cannot explain that. Next, I have to other key contributors in my talk, in my this board. One the Vijay Lakshmi Gupta is, and another computer she is sitting over here, Amlan Das. He is a really genius. I don't know if you will accept him as a genius, but myself and my wife accept him as a genius. He is a very intelligent guy, and we have an outstanding contribution in my research, and we publish a lot of papers together. In addition, Arnav Ghosh in Amulak, others I don't want. And I have to give a credit to Lester Lau, who gave us the mice model. Anirban Maito is a MD Anderson. And Daniel Hoff, you know, he discovered the drug that's called gemcitabine. And he's our collaborator. So I said that I'm lucky because I have these people all together, you know. Without them, I cannot do anything. Okay, you know the pancreas. Pancreas is a very 6 inches long in our body behind the digestive tract. And it divided into 3 parts: head, body, and tail. Pancreatic cancer develops anywhere in the pancreas, you know that. Body and tail is 20-25% cancer develop. The rest is the head cancer. And if you have the head cancer patient, you can easily tell the person has the head cancer because he will get the jaundice. Your face will be yellow, urine and stool will be white. So like a jaundice patient. But other 3 cancers, if you patient get it, there is a belly pain, constant belly pain and back pain. So if you are at age of 50 or above, if you have a constant belly pain and back pain, you should contact your doctor. You might have nothing, or maybe the pancreatic cancer. Among this, you know, so we find that the 5-year survival of the pancreatic cancer is only 5%, but it is really very high. Generally, if after diagnosis, patient can survive for 6 to 7 months. They will die. I mean, there is no medications for pancreatic cancer. So, if you look at the pancreatic cancer, it is 2 types of pancreatic cancers. One called endocrine pancreatic cancer, other is exocrine pancreatic cancer. If the cancer occurs in the cells that's like islets of Langerhans that produces hormones and other things, this cancer is not it's a deadly cancer, but not like this kind of exocrine cancer. The secretory pancreatic enzymes into the pancreatic duct that generally occur in the duct. That's why it's called ductal pancreatic cancer. So among these 2 cancers, this is the relatively less aggressive than this, and this one is this cancer died our iPhone owners. What's his name? I forgot. Job. He had this endocrine cancer. That's why he survived for 5 years after having the cancer. And most of the patients, you know, just yesterday, one of my families called me and told me that diagnosed as the pancreatic cancer stage 4. That means he will survive for 6 months maximum. Okay, next. Like other cancer, any cancer, if you look at, that's a very sequential process. All normal, precancerous, cancerous, and then metastasis. It's every cancer, doesn't matter. Pancreatic cancer is also sequential cancer. You can see the normal duct, PAN1, 1B, 1, 2, 2B, and PAN3. See? And then metastasis. And you can see multiple mutations are there. Very interesting thing. You know, the pancreatic cancer is called cold immunity, immunotherapy, because there's no immunotherapy drug will work in pancreatic cancer. Having all kinds of mutations, but still, we don't know why. So the oncogenic KRAS mutation are the major event in pancreatic cancer, followed by p53. In human, you can see both KRAS mutation also. I'll come and show you how the same 2 mutations can develop the cancer in the mice model. So pancreatic cancer ecosystem, like all our ecosystem, every cancer has a very nice ecosystem. In pancreatic cancer, if you look at that, there is two, let me show here. There's two different things, is called dysplasia. So let me briefly explain the dysplasia. It's called fibroblast cage. Most of the cancers, they don't have the big fibroblast cage, but pancreatic cancer and triple negative breast cancer, they have a very nice cage and cancer sitting over there, so the drug cannot enter cannot hit the cancer cells because of this cage. This is called dysplasia. In pancreatic cancer, dysplasia is very strong. I will show you the pillar, and then they have extracellular matrix protein that also plays a role in dysplasia. This is the very poor angiogenesis. In both triple negative breast cancer, you will see very poor angiogenesis. In pancreatic cancer, almost very weak blood vessels in pancreatic cancer. So that's why drug cannot enter into the two reasons for the this big reason is this, and this poor angiogenesis. The blood cannot enter. So we have a blood. We have a drug, but we cannot treat them because we cannot target the pancreatic cancer cells through the drug. So that's the very weakness of this part, and all these things, this part, this dysplasia and this angine triggering this. Okay, one thing I forget to tell. This angiogenesis is controlled by the fibroblast. That's called pancreatic islet striate cells. That is activated by the KRAS and develop the dysplasia. It's a very nice cage, and this is controlled by KRAS mutations. And KRAS mutation is not only control the dysplasia, control the tumor growth by regulating all this, but cannot control the immunosurveillance. Let's go. So, what is KRAS mutation? I'm not going into details. KRAS, we have the KRAS, always we need to maintain the homeostasis model. Things, pancreatic cancer growth, development, and all these things. But uncontrolled KRAS production is due to the mutation. And we have seen these three different mutations, G12C, G12D, and G12R. Among them, G12D is very common in pancreatic cancer. Almost 80% G12D mutation we can see, other is very few. And now in American newspaper, they're talking on all the journals, Nature, we developed the mutant KRAS targeting mutation, but they developed the GRAS 12C, that is only 2% in the pancreatic cancer. So basically, we don't have any drug. So KRAS historically been impossible to target with drug treatment. Another reason is the KRAS protein is so smoothly proteins, you cannot make any small molecule to fight with them because other protein cannot bind. They're so smooth, very smoothly, So very targeting ecosystem is very difficult. And if you look at that, in what way mutant KRAS work? Mutant KRAS works at different pathways. If you show busy slide, if you look at the NFK pathway, AKT pathway, JNK pathway, all different pathways, and they function differently: endocytosis, survival, proliferation, transformation, invasion, everything. So KRAS is a very, master protein, this mutant protein. So, and also the KRAS is working dysplasia and drug resistance. So what do you do now? So that's why I gave the name is the second kind of impossible. Because people think that it is a possible. No, it's a second kind of impossible. It's not a first kind of impossible. Because scientists always think that, oh, we can do it. So it's a first kind of impossible. But it is a second kind of impossible. That's why I'm protecting the scientists sitting in the front line. Oh, we can do everything. No, that's why it's a very sweet. So what I use, the second kind of impossible. Let's go next slide. So then we are always, love CCN family protein. So we try what is cellular communication network factor CCN1 anymore. So I think if I'm not wrong, Amlan started first. but he is very lazy, so he could not finish the work. So he came over here, then we have to finish it. So we found that KRAS is basically very expression, CCN1 expression is very low in pancreas compared to other. Very low expression in pancreas by RNA-seq. And what we did, I'm just briefly discussing because like if I start, it will take 2 hours. And already one lady is sleeping here, I can see. So what research is being done in Kansas City on CCN1? We found that CCN1 promotes EMT and stemness and desmoplastic reaction. What is the EMT? Epithelial to mesenchymal transition. So EMT is a very physiological process. We need it for the development of our body. But EMT in pancreatic, any cancer, that means it promotes the invasion. Cell can go from one place to other of the other side of the body. Next, we have seen this. I will show you the data. Role of CCN1 in drug resistance. CCN1 is downstream target of the mutant KRAS and regulate the KRAS activity via feed-forward mechanism. CCN1 help promote KRAS-mediated PDS growth and target nanovascular. That data I will briefly show you. So if you have any question, please feel free to ask me. Okay. So what is CCN1? CCN is the family. Cell is called cellular communication network. CCN family. There are 2 groups. Group 1. And there's a group 2. In group 1, CCN1, CCN2, CCN3, and CCN4, CCN5, and CCN6 is the other group. And CCN5 are which 2 we already plays a very big anti-invasive role in breast cancer. And CCN1 now I'll discuss about the pancreatic cancer. Let's go. There's a function of the CCN1, CCN family genes. There is a 4 modules. One is the IgBBF, WVC, TSP, CT domain they have, and all these things. I don't want to go to the busy slide. You know, if you want, you can read this our review article. You'll find details. Let's go to the other thing. And CCN1. Also, you find that CCN1 and CCN3, all they are connected with the different oncogenic players like YAP1, FN1, Notch1, TGA beta 1, all these things. And they work together. It's a playing game together. So now the differential expression of the CCN1 mRNA protein normal pancreas and pancreatic duct. Why we think the CCN1 plays a role in cancer. Look at the here. This is the normal. Grade 1, grade 2, and grade 3 doesn't matter. And if you have the expression profile, you can see the CCN1 expression in group 1, group 2, group 3. Also, PAN1, PAN2, PAN3, you can see the start expression over here, PAN2, and onward. So CCN1 is expression you can find very early stage of the pancreatic cancer. Period. Then we decide to see the expression profile in the different cell line, and it is a northern blot long time before we did it. SIR61. Initially, CCN1 name was SIR61, and we have seen these 2 cell lines, BXPC3, CAPAN1, ASPC1, and PAC1. These 2 cell lines highly express the CCN1, and also we confirmed by the Western blot analysis. Next, we do what is a function? I mean, we thought that so why CCN1 is what expressing in pancreatic cancer cells lines. So we did it. That's called phosphoproteomics, single cell phosphoproteomics. We did it. And we find that here is that downregulation of pro-proliferative signaling in PANC1 cell following CCN1 knockout by a single cell this should be phosphoproteomics. And we find that most of the cell cycle regulatory genes here are downregulated once we turn off the CCN1. So CCN1 is basically plays a vital role in regulation of cell proliferation or differentiation and in transformation. So CCN1 expression and epithelial mesenchymal transition. As I mentioned earlier, the EMT, if you look at that, there's a PXPC3, no expression in CCN1, but CCN1 and ASPC1, PANC1. And what we did here, all the markers we checked, that epithelial marker as well as mesenchymal marker. And you find that in ASPC1 and PANC1, CCN1 positive cells, the E-cadherin, beta-catenin, creatinine is downregulated compared to other two cell lines. On the other, in contrast, you can see vimentin, Notch, OX4 are upregulated, which are mesenchymal markers. So it is an indication that in these cells, mesenchymal markers are upregulated, but epithelial markers are downregulated. Okay, so what? Up and down. So we have to prove. We have to do some experiment. Is that right? What we did, we turned off the CCN1 from the genome of the PANC1 cells. And first we see the structure. If you look at that mismatch shRNA, okay, here, let's go here. shRNA, mismatch SAR61 shRNA completely disappear, knocked down here. In mismatch shRNA, the cells are very mesenchymal type. If you look at that mesenchymal type, the moment it turned off, it's become round epithelial type. Here is we see the migration invasion, and it goes down after knock down the CCN1. Migration and invasion is significantly reduced. Go back to the next slide. Okay, here is that. So I'm not going details about that, but I'm going to say something about the mechanism. So we know the I think you are aware of the microRNA. MicroRNA plays both positive and negative roles. Most of the cases, microRNA plays a negative role rather than positive roles. So we check the microRNA status in this after knocking down the CCN1, and we found most of the mesenchymal and epithelial migration marker or meal are downregulated or no effect when we knock down the SAR61 or CCN1. I will come later and I will show you the exact functional significance. So now here's the experiment. Now you can ask me, so again the question is, when you do the in vitro experiment, anyone can ask me, so what? If it goes up and down, any functional what is the effect in the real world? So what we did, what first we tried, we separated the interesting part in MDMB231, that's called breast cancer cells, or in pancreatic cancer, PANC1. If you pass through the cell sorter, you will get two different kinds of cells. So we get the name, one is the NSP and another called is SP cell line. What is the SP and NSP? If you look at the structure, most of the NSP is the epithelial type, round separate. And most of the SP cells are mesenchymal type. And we check the CCN1 expression or SAR61 expression. SP is overexpressing the SAR61. NSP is very little expression. So, and all other markers, I don't want to go details, you know all these things already. We injected the node mice. Keep in mind, it's only 500 cells. It's not like 5,000 or 5 million cells. Only 500 cells. We injected the node mice here, and also in the NSP cells, in the another mice. What do you find? Within, I think it's after 15 days of injection, we found a huge tumor in the node mice, but no tumor in NSP. Number of mice, 9 mice used, we got the 9 mice tumors. NSP, SAR61 negative mice, 7 mice, no tumor. We knocked down the SP, 5 mice, no tumor. So it's a clear indication that SAR61 or CCN1 plays some role in tumor growth. So in summary, one, we can say that SAR61 induced EMT, stemness, and tumor growth. And if you block the SAR61, then you can inhibit the tumor growth here. Up till now, we published in 2011. Okay. So next is the CCN1 silencing moderate the SHA signaling pathway. So this is the one pathway we discuss about that. What is the another pathway? It's a very established pathway. The Hedgehog signaling plays a vital role in pancreatic cancer, mainly dysplasia and others. So we decided, so what is the effect of CCN1 on Hedgehog signaling pathway? We found that in PANC1 cells and MIA-PACA2, CCN1 status, when you turn off the CCN1, no beta-catenin, SHH, it goes down. Look at that. Huge expression in normal condition in parental cells. Knockdown expression is almost 80% gone. Here is no expression. So, and also we signaling pathway, we check cyclin G1, PAT, all these things. I don't go to details. If you want to have a question, I can ask the answer, all these things, because time is important. So we summarize here that CCN1 binds with the integrin, alpha B, which is integrin, turn on the JAK, and this way they turn on the SHH signaling that plays a role in tumor growth progression, cell motility, EMT, and proliferations. Because we know that's already established, so I haven't used this one. I think it's published in JBC 2012. Still, if you want, you can see this the mechanisms. Next, CCN1 in chemoresistance. This is very interesting paper, published this one. Normally, if you look at this networking, CCN1, 61, linked with different genes that are associated with the chemoresistance. That's already reported data, link among several chemoresistant gene signature pathway and CCN5 expression. You can look at that. We published this one is 2019. So, role of CCN1 in programming of cancer stem cells and drug resistance. So, it plays some role in cancer drug resistance. So, you have to talk about stemness. I think Amlan did this work. Is that right, Amlan, you did it? Yes, you did. So, PANC1 cells, positive PANC1 cell, negative, and all these things, CD33 and CXCR4, they checked in these two cell lines, and really it goes down. CD133 is a very good marker for pancreatic cancer cells for chemoresistance, and also this is the CXCR4. So Amlan did experiment, and they found that significantly reduced the CD133, CXCR4, and all these things. And also we did that SARS61. So finally, from this experiment, we find that the CD133, CXCR4, and CCN1, these three combinations promote the cancer stem cell proliferation, self-renewal, and unlimited growth, tumor growth. And you can see the dysplasia. But if you turn off the CCN1 here, you might get the growth some, but no dysplastic reactions. So needed for dysplasia or drug resistance, you need a SAR61 or CCN1 expression. So how it works, I will come to that. So what we did here, this technique is also patented, artificial in situ dysplastic reaction. What we did, this is an agar gel, agar ring, and we put the PANC1 cells here, and outside we give the human pancreatic stellate cells that can produce the dysplasia. So here is the expression profile. I'm not going to do that. What happened? Why you did that experiment? Very simple thing. So back, sorry. Why you did this experiment? Because normally fibroblast cells are inactive. And how do you figure out that it's active? If you get the alpha smooth muscle cell expression is very high. The alpha smooth muscle expression is the very good marker for active fibroblast cells. So the moment we culture together here, this is the indirect culture, we find that this human stellate cells is very active. The green color you can see is a active fibroblast cells. And this one very less when you have a negative SARS61 negative PANC1 cells. So it is a very clear in vitro indication that to make desmoplasia, or other way, if you make a ecosystem is different than normal, you need a SERT61 overexpression. And there is another studies we found that. So how it works? So we find that the CTGM, another sister of the CCN1, is required to activate the desmoplastic reaction. So CCN1 talk to her sister and turn off the angiogenic, desmoplastic process. I'm not going to details on this busy slide, but that's the whole thing. So we conclude like that. Pancreatic ductal and epidiac cells, they produce the CCN1. These CCN1s go back to the epidiac cells, turn on the CTGF, and also it goes to the fibroblast stellate cell, turn off the CTGF, and activate the stellate cell. That we published in the 2019 in molecular cancer therapy. So next we can come pancreatic cancer cell resistant to gemcitabine. As I mentioned, the gemcitabine we started because one of help told us to let us check what is going on in this gemcitabine. And we find here, if you look at that, SERT61 positive or CCN1 positive and negative cell in pancreatic cancer cells, you can see the gemcitabine effect is increased significantly. If compared with this, here also, viable cells is a different cell line. It is a PANC1, the SERT61 plus cells, SERT61 minus cells, different doses, 0.1, 0.25, dose dependent effect. You can see here, you can see the another cell line, ASPC1, and there's a gemcitabine different doses. It's like that, we did it. And then we did in the SP population and non-SP population. Non-SP population, we didn't find any difference. So, but in SP population, the effect is significantly high because I turned off the CCN1. Let's go next slide. Here we can show this normal cell line, which is completely normal pancreatic cells. We found no effect. Okay. So, what is the mechanism? Gemcitabine, normally is an inactive drug. When you inject into our body, it's an inactive compound. It will go intercept the cells. There is two different enzymes. One of them is the DCK. DCK is one of the enzymes that activate the gemcitabine, inactive form to active form of the gemcitabine. That's the mechanism and it works. Unfortunately, in pancreatic cancer cell, gemcitabine worked for a while and then disappear because DCK cannot work. Why? Look at this picture here. This is the SERT61 expression. PANC1 BXPC3. Here is the BXPC3 DCK expression. In PANC1, this DCK expression is very low as compared to the BXPC3. Over here, we showed that SERT61 DCK different cell lines, and of course here the DCK. We found this basically. Simply we can say SERT61 expression and DCK expression is reverse, opposite. If you have a more SERT61, less DCK. If you have a less SERT61, more DCK. So we did another experiment. So here we put the DCK. Here we checked this one. We injected the DCK vector and vector alone. We found that DCK is overexpressed as after that, and we find that gemcitabine effect is increasing pancreatic cancer cells if we artificially overexpress the DCK. So it is very clear that DCK plays role, cannot work in our body because of SERT61. So go to the next slide. So it is in vitro data. Of course, you will ask this in vivo, what's going on in vivo? Very simply, we did the mice. Look at that, SERT61 positive PANC1, SERT61 negative PANC1. We injected, we got the tumor, we gave the gemcitabine, no effect. Here, SERT61 knockout cells, we give the gemcitabine, we found the effect. Look at that. So gemcitabine, we can activate the gemcitabine in our body if we turn on, turn off the SARS61 in our body. So basically, pancreatic cancer patient, they are giving the gemcitabine. Still, there's no medicine. They're giving the gemcitabine. Doesn't matter if you go in best medical school in America or some village in India. Same drug, they will give the gemcitabine. And patient will give for a couple of days. After 6 months, the patient will die. So if we activate the DCK enzyme, we can treat the patient. At least we can save the life for a while. Okay. So here so you can see over here. Look at that. There's a normal pancreas, highly aggressive pancreas with dysplasia. Dysplasia here. Here is the after treatment. You can see knockout patient, no dysplasia, and tumor growth regress. So I'm not going to details all these things. You know, if you want, or other enzyme we checked, and we did in the 5 mice, and we found the result. Oh, it's very this slide. So next go. So basically, what do you find? Gemcitabine active to what? Kill the tumor. But CCN1 block the DCK, it cannot work. Very simple things. So if you want to activate the gem, you need a DCK. So to do that, you have to turn off this buggers. Okay. Next, KRAS and CCN1 story. I know you're tired. So this is things. You know, there's a new term used called pancreatic cancer cells are KRAS addicted. You know, a lot of people are addicted to something, you know, movie addicted, YouTube addicted. So all sitting over here, KRAS cells are, pancreatic cancer cells are KRAS addicted. So addiction is not bad because everybody is sitting over here. How many? All are addicted. Okay, something. So KRAS is very much addicted to KRAS, pancreatic cancer. To destroy them, you have to stop this addiction. So what is the role of CCN1 in addiction? That's our work. And this paper we are communicating. Also, Amlan is also author, communicating this paper in Nature Communication. It will go next week when it will go back. It's a very good work. I think if you don't like, I cannot, I'm sorry, but I will like it. Okay. Look at that. Relation between SARS61. Here is a pancreatic cancer. It is a Kaplan-Meier analysis. Here you can see this SARS61, P53, and KRAS. Huge. Or when you have 3 mutations here, overexpression of SARS62, CCN1, P53 mutation, KRAS is a huge. The stage 4. You in 100% patient you will get it. Doesn't matter. You will get it. So if you target only one, suppose you target this, then you will get the pancreatic cancer. If you cannot target the KRAS, unfortunately. So leftover is CCN1. Can I control this thing? Here's the KRAS G12D, as I mentioned, that regulate the CCN1. We find that CCN1 expression is regulated by KRAS mutant, not the normal. KRAS mutation, SARS61 overexpression is due to KRAS mutation because if you turn off the KRAS, if you just put the wild type KRAS in the pancreatic cancer cells, any mutant pancreatic wild type, you will see SARS61 goes down immediately. Cell growth, because you are destroying the addiction, the cell growth is slowed down, no transformation, no invasion, no migration. KRAS is that thing. So now we have this tree, and here we can see the KRAS, B-explicitly KRAS wild type, normally wild type. We put the mutant and we found exactly reverse effect. And we check the KRAS regulated CCN1. This is called colony formation assay. We find that wild type has very few colony, while mutant has a huge colony forming ability. But in presence of CCN1 protein, I added the CCN1 protein. Just dump on the culture with CCN1 protein. We saw the colony formation effect is going up and going down if we add the antibody because it's secreted protein. So we find this result. Next we did. So then we check. So if this is the case, then what's the relation with the CCN1 and KRAS? If we turn off the CCN1, what's the status of the KRAS? And we find that if we turn off the CCN1 expression, CCN1, we find the KRAS goes down. So they are crosstalk each other. So we find exactly we did it in the activity where phosphoAKT. This is also ambulance SWOT and phospho-ARK. We found that CCN, if you turn off the CCN1, you can turn off the KRAS, AKT, and phospho-AKT because ERK and AKT is the downstream target of the KRAS mutant. If you do so, we conclude that CCN1 and KRAS is crosstalk, we feed forward each other or crosstalk. So now we can ask what's the mechanism? How KRAS regulate the CCN1? We found that, we checked this one, the promoter of the KRAS, and we find that there is sequence homology in the CCN1 promoter with his mean 145P. And this is the mean 45 is the tumor suppressor microRNA. The expression profile of the mean in different cell line, normal, huge, rank 1, ASP is 1, KBC. KBC is the another mouse cell line, no expression. So what we did, we just add the mean 145 and check the status. Mean 45 gene, we transpected them in the plant one cells, and we find that SAR61 level goes down. So mean 145, and it's already reported that mean 145 is KRAS is regulated mean 145. So accordingly, we check that. So KRAS, normal KRAS, turn on the 145, turn off the CCN1. Mutant, turn off the 145. SAR61 goes on. And so from this experiment, if you look at this whole data, you can find this one. Wild type, mutant, and you can find the data over here. I am not going to say. So basically, in figure E, we conclude that wild type KRAS, that is we have right now, possibly because pancreatic cancer took 18 years to detect. So maybe we have the pancreatic cancer and we don't know. After 18 years, after 10 years, and 5 years, or maybe after 5 days, we will see maybe the stomach pain start. So everyone is, that's why Bert Vogelstein told, everyone are cancer survivor. Everyone sitting in the room, all are cancer survivor. So we can consider KRAS wild type in normal pancreas, turn on the mean 45, turn off the CCN1. KRAS wild type in the tumor, turn off the mean 145, CCN1 upregulate, regulate the KRAS. So it is like this way they play out. So effect of CCN ablation on the PDA growth and progression. That is another part. I hope you will like this one. Okay. Generation of CCN1 conditional knockout mice. Now we go to the mice. We generated knockout conditional. We made a pancreatic cancer, that's CCN1 only turned off in pancreas. So how you did that? This is the CCN1 flox mice crossed with the PDX1 CRE. What is the PDX1 CRE and what is CCN1 flox1? The CRE can cut this one and remove the gene. This is a CRISPR method. Okay. What PDX1? Why you add the PDX1? Because PDX1 only CRE will only work in the pancreas, not anywhere in the body. Just it will, when it will enter the pancreas, if they find a CCN1 flux bug, it will cut it and remove that one. So pancreas, only pancreas is CCN1 negative and entire body is fine. We do that and we generated CCN1 flux box PDX1 pre-mice. It's called CCN1 conditional pancreatic specific knockout mice. Okay. And how do you confirm it? Look at that. Just we collect the pancreas and we do the microdissection and do the PCR, and we find that this one is missing in this mice. Not this mice, not even this mice. Only this mice you can see the missing. KRAS is completely gone. Okay, now what we did, we find another mice. You know everyone. This is the called KPC mice. What is the KPC mice? This KPC mice, they have the KRAS mutation, P53 mutation mice. They cross with the PDX3 mice. So they will just different conditions. They will put the mutant KRAS mutation, P53 mutation into the, because it is not lox, it is F-lox. So it will introduce the KRAS mutation and P53 mutation and removing the wild type and mutant type. Normal P53 and normal wild type they remove and they will put the mutant KRAS and mutant P53 device. So you will get the mice. That's called KPC mice. Okay, after having this. K means KRAS, P53, C, the PDX3. And in this mice, you will get 100% pancreatic cancer. You can see 4 to 6 weeks pan-in-1. Locally invasive after 8 to 12 weeks, 16 weeks you will get metastasis. And weight loss, dysplasia, cataxia, malignant ascites, metastasis, everything the symptoms you can get in human. Now what we did, we took this mice, cross with PDX, we made a KPC and cross with the CCN1 knockout mice. And we got the next generation. What do you find? This one producing days. But when you cross these two, we get no pan-in-1, no local invasion, no metastasis. Nothing. And here is the data. Wild type, pancreatic weight, it is a pancreatic weight. KPC, huge weight is after 6 months. KPC SAT61, very close to the normal. Here you can see the section, 3 weeks, 3 months, pancreatic cancer. Here you can see the dysplasia, endpoint. We consider 10 to 12 weeks the endpoint. For the sake of the paper publication, we consider 10 to 12 weeks. If the mice will survive 10 to 12 weeks, is live, not consider the end. Sure.
Sorry to interrupt. So the development is normal, it's not CCN1.
Yeah, exactly normal. No problem. No problem. Yes, which one? I can bring this slide.
No.
Yeah, it's pancreas. Normal pancreas has no effect. If you have a tumor, PanQ1,
Delta pancreas.
or delta
Pancreas is normal.
it's normal. That's what we check. We don't have this data. When we publish the paper, we already in our data we can see. Yeah, no effect. Here you can see the immunohistochemistry, SAT61, no SAT61 here. And the survival, you can check this one. You know, when you find in the 30 mice, the data is so good to believe. How come? Then we did in 120 mice. And you know that developing, if you work in mice, is so difficult, take several years. And then we check this one and we show that lifespan is they increase the lifespan. So we need, basically pancreatic cancer patient, we need, instead of dying for 6 months, 6 years, it's better, is that right? So, and it's look at that metastasis. KPC 6 months, huge metastasis in liver. In normal knockout, nothing, almost nothing. 4 out of 35 mice with liver metastasis, only 4. We had 11 out of 35 with liver metastasis. Okay, you can see this. So, basically, we can conclude that this is the one, KRAS, work through this one, RAF, MMPK, ARK, all these things, and this, but SAT62, the SAT61, and P53, and if you turn off this one, you can get nothing over here, no dysplasia, nothing. So, now we just talking about nanoparticle. I know people are, someone is interested, someone is not, but nanoparticle is a very novel, new technology. This one is we just published the cover page of the journal, Molecular Pharmaceutics. So what we did here, ARK inhibitor, we use the first time we use the ARK inhibitor because ARK inhibitor is the downstream of the SAT61. So we use the SAT61 in Mutant in a nanoparticle. And nanoparticle is also, we made the nanoparticle is a very specific, targeted. We put a IRGG over there that is tumor cell specific. And then, because why it is very specific in pancreatic cancer, because IRGD bind with the NRP1, neuropilin 1, which is overexpressed in pancreatic cancer and also in triple negative. That's why we have another paper. Amlan is the first author. I think you're the first author, the corresponding author also, is that right?
Yes.
Yeah, EGC. We same and use, and over there we add the IRGD and the folic acid, whatever you want, and then here's the IRGD, and then we inject it into the, give it the mice also and in vitro. It will just move around the whole body. It will not go anywhere. It will not release the drug. The moment it will get the tumor, it will bind with the NRP1, enters into the cell, into tumor, and then again start to look for the hypoxic area, low pH hypoxic area in the tumor. And you know the hypoxic area, low pH is an indication of the stemness, highly or aggressive cell line. And then once they find this one, they get the smell of the hypoxic, they release the drug. So we have in this paper, we have two flower-like capsules. One is the gemcitabine, one is the ARC inhibitor. And then they enter into the cell, the tumor. And once they find the pH, low pH, normal pH, they release the drug and it works like crazy, I mean, you do not know, side effect is very low because ARC inhibitor is a very toxic. That's why it is clinical trial stop because of the toxicity. And we find the toxicity is almost zero in mice at least. So we submitted the patent for that and it's in the process now. Finally, we find another thing I've said, the xylotonic acid. That also is an inhibitor of CCN1. We can inhibit the CCN1 through this xylotonic acid. And recently we found silipilin also that can inhibit the block the CCN1 expression. And that is also we did the nanoparticle base. And then now we have another nanoparticle that is called monitoring nanoparticle. That's a very simple nanoparticle. We put a chips in the nanoparticle. And then you can inject the chips and there's a barcode. So your phone, you can monitor the nanoparticle. You can see the nanoparticle is moving in the mice and your phone can tell you, oh, okay, where is the nanoparticle? This nanoparticle is now close to the tumor, is now close to the liver, you can tell that. So it is a new technology, new monitoring process. So we are using that. So this is my last slide. And this is my rabbit. He passed away 2 years ago. Her name is Yasmin. He spent a lot of time with me. Okay. Beautiful cat. Okay. So thank you. Now, any question? Yes.
Your last slide, you showed the nanoparticle delivery. You showed the co-delivery of the remdesivir with ERK. So still in your previous slides, you said that remdesivir will be only in inactive form and then you need an enzyme to be inactivated, right? So when you do a co-delivery, how does the remdesivir get activated?
That's the weakness of this work, but we did it together. The problem is that SAR61 or CCN1 is basically, if you go my fourth slide, I showed that there's a ASP population and SP population. In pancreatic cancer, not all the cells at primary tumors are secreting CCN1, mainly the stem cells and aggressive cancer cells. In the real world in human, if you have the pancreas, mostly stem cells, and this is our hypothesis, we don't know yet. So ARC inhibitor just kill all that cells that produce the SAR61.
Still, it's more toxic when you get into the co-delivery. If unless it is a dose regulated.
No, but the ARC inhibitor is a very toxic, true. But once you put in the tumor, it is very localized, it's kill the cells. Of course, some toxicity is there. I cannot say, even if you take the homeopathic medicine, you have some toxicity. Okay, but you cannot measure it. So of course it's toxicity, but at least we can control. Now what we'll do now? Now we are doing that. That's why we have a xylotonic acid. So we are doing the ARC inhibitor, one flower, another flower we are giving xylotonic acid, and we were injecting the mice. And then after 7 days, we are giving the gemcitabine. So what is the effect? Can I, without encapsulating the gemcitabine, can it work? Because we are destroying the desmoplastia. We are destroying the SIR61 producing cells. So hopefully now the gemcitabine should work. And we did it. And I have in mouse model, we have a very good results. But we don't know the human, human are from our, maybe.
Okay, Raghav, just I can add some points. So I just add some points on your question. There are two aspects of this nanogardening. So the first one is targeted. So it is being targeted to cancer stem cells only. So if you go there, release whatever the product is being encapsulated. And secondly, there is a low expression of the enzyme in pancreatic cancer, but always there is a basal level expression. It's not that the expression is very neat. So now when I am putting a combination drug here, if the ART inhibitor is very low dose, it's already being active. And whatever the gemcitabine is there, the low expression of that activating enzyme, and it is turning on the gemcitabine. Now, before the scenario was that we were putting gemcitabine, but that is not activated. But when this delivery is very much targeted, now it is joint action. So these are, so number one, the toxic dose of the ART inhibitor, it is also we are decreasing that. And number two, whatever the little gemcitabine is deactivated, that is enough to kill the cells along with this ART inhibitor. So that is the benefit of this targeted nanocarrier. So that's a very, yeah, so we have a very nice solution. But the basal level expression of the enzyme, whatever it is, has, that is very, very sufficient to activate this low amount of gemcitabine to activate this.
Any question? No?
There's one question on my phone. What makes MAIL 145 go down? Is this a prerequisite for pancreatic cancer to originate, or its down regulation is dependent on the mutant KRAS G12D? What is the status of MAIL 145 with CCN1?
Can you read again?
Okay. What makes MAIL 145 go down?
145 go down, yes.
Go down. Is this a prerequisite for pancreatic cancer to originate, or its down regulation is dependent on the mutant KRAS G12D?
No, mutant KRAS, yes, mutant KRAS down regulates the 145 and wild type up regulate the 145. So that's why it turned off the, in normal conditions, it up regulates the 145 and then down regulate the CCN1. In tumor, mutant blocks the 145, the CCN5 upregulate, and this CCN5 again turn on the mutant.
So it's dependent.
Yeah, of course, yes, of course. Yes.
And what is the status of MAIL 145 in CCN1 knockout mice?
In CCN1 knockout mice, see. Okay, I have the data. If you turn on the 145, or you're talking about what is the status of the CCN1 knockout mice, it is less because CCN1 control the mutant. So mutant, if you knock out the CCN1, if you knock out, you also turn off the mutant KRAS. Obviously, you will get more this quality. Yeah, 145. Is there very much linked? Yes. Any question? No? Okay, thank you.
Thank you. Fires to my both surgery and yeah, please request
Oh, sorry, I'm just. Oh, thank you.
was an excellent presentation. Thank you so much for taking the time off to come and visit
Oh.
and spend time with us.
I'm very much. Bye. You like it?
Yes. Great.